Welcome back, Focus Learners, to another deep dive here on The Explainer. You know, every single second, hundreds of thousands of gigabytes of data are just blazing across the globe. Today, we're pulling back the curtain on something we all use, literally every single day, but honestly rarely think about: the absolute miracle of global internet communication. We totally take it for granted that our devices just seamlessly talk to each other, right? But the underlying architecture making that possible, it's a fascinating, highly structured ecosystem. It's actually a masterpiece of engineering that relies on a very specific set of rules, or protocols, working together in just perfect harmony.
Okay, let's dive into this. Picture this. You're sitting at a coffee shop in Toronto, Canada. You compose an email, you hit send, and almost effortlessly, that message pops up on the screen of a colleague in Pune, India, in mere milliseconds. But how? How on earth does that data travel across a massive, chaotic, decentralized network of totally diverse hardware across oceans and continents without getting completely lost? Well, to understand how these vastly different systems manage to cooperate and route our information with such crazy precision, we have to look at the foundational language of the internet.
So here's our structural roadmap for today. We're going to look at 1. The Internet's common language. 2. The birth of TCP/IP. 3. The four-layer protocol stack. 4. Encapsulation, which we'll call the envelope analogy. 5. Directing the traffic. And finally 6. The invisible framework. Let's get right into it.
Section 1. The Internet's common language. The absolute need for a universal standard.
Think about it. The physical infrastructure of the internet is incredibly diverse. You've got different computer manufacturers, different server types, totally different operating systems. For any of this to actually work, these disparate systems somehow need a universal standard to talk to each other. And this brings us to a really cool concept called protocol independence. Just think about the sheer variety of devices out there today. You have Unix servers, Windows PCs, Apple Macs, and they all function completely differently under the hood. But because network devices are compatible at the physical and data link levels, they can run completely different operating systems over the exact same physical cabling. Protocols essentially act as a unifying common language. So why does this matter to you? Well, it means your Apple smartphone can seamlessly load a web page that's hosted on a Linux server without you ever noticing they speak completely different native languages. As long as the device speaks the protocol, it doesn't matter what hardware or software it's running. It can communicate with any other device on the network.
Moving on to Section 2, the birth of TCP/IP, basically organizing all the chaos.
To really appreciate this universal language, we got to set the scene back in the late 1960s and early 1970s. This was the era of the ARPANET, the granddaddy of our modern internet. And let me tell you, it was a bit of a Wild West landscape before a standardized internet working language existed. The journey really started around 1969 when Steve Crocker formed a networking working group alongside internet pioneer Vint Cerf. Moving into the early 70s, the big goal was figuring out how to interconnect these packet switching networks that had completely different specs. This research, spearheaded by Bob Kahn at DARPA and Vint Cerf at Stanford, was literally a race against time to standardize early computing. It all culminated in December 1974 when they published RFC 675, officially outlining the transmission control protocol. Then, after years of testing and modular redesigns, this monumental shift happened. In January 1983, the ARPANET officially scrapped its older protocols and adopted TCP/IP version 4 for production use. And just like that, the core component of the emerging internet was officially born.
All right, Section 3, the four-layer protocol stack, how we simplify the incredibly complex.
So building a global internet working system is a massive, massive headache. To solve this problem, engineers created a beautifully structured hierarchy, what we like to call the protocol layer cake. The TCP/IP protocol suite is built around 4 distinct layers of technology. You've got the application layer up at the very top, followed by transport, then internet, and finally link down at the bottom. The sheer brilliance of this layering is that it segregates networking into smaller, highly specific functions. So the application layer handles things you interact with, like web browsing and email. The transport and internet layers provide the universal services to actually move that data, and the link layer? It just deals with the physical network interfaces. Because of this structure, no single system has to understand every single detail at every level, which makes moving data from point A to point B incredibly efficient. Diving into that transport layer specifically for a second, we see that the internet actually has different tools for different jobs, depending on whether you need perfect reliability or just sheer unadulterated speed.
This layer is essentially the application's interface to the network, and it primarily uses two main protocols, TCP and UDP. TCP, or Transmission Control Protocol, is connection-oriented. It absolutely guarantees an ordered, highly reliable transfer of data, which is exactly why we use it for HTTP web browsing and sending emails. I mean, you want every single word of that email to arrive, right? UDP, or User Datagram Protocol, on the other hand, is connectionless with absolutely zero delivery guarantee. I'd actually tell you a joke about UDP right now, but I can't guarantee you'd get it. So why even use it? Because it is blazingly fast and operates with way lower overhead. It's a go-to protocol for things like DNS or real-time streaming, applications where speed is everything, and a drop packet here or there isn't going to ruin the whole experience.
Section 4. Encapsulation. Let's look at the envelope analogy.
Let's move to this and see how this all builds. How do these 4 layers actually wrap around our data? It literally works just like a corporate mailroom. When data travels from the upper application layer down to the lower link layer, it goes through this Russian nesting doll process called encapsulation. Let's break it down. In step 1, your email app creates the message itself. In step 2, the transport layer takes that message and stuffs it inside an envelope. It adds a TCP header. Then in step 3, the internet layer takes that envelope and puts it into a slightly larger envelope, adding an IP header with a final destination address. And finally, in step 4, the network interface puts the whole thing into a final outer envelope with a layer 2 header. Each layer encapsulates the data with a brand new envelope that's necessary for the very next stop on its journey.
Section 5. Directing the traffic. How we actually move these packets globally. Okay, so our data is fully packaged up in all these layered envelopes. How does it physically navigate the massive global web of network devices and routers to actually reach India? Think back to our email from Toronto. As it travels independently across the network, it relies on something called hop-by-hop routing. An intermediate router receives the packet. But here's the kicker. It doesn't rip open the inner envelopes to read your email. It acts exactly like a middleman mailroom. It only looks at the outer envelope, specifically the destination IP address in the internet layer header. And based on just that address, the router figures out the next best path and dynamically forwards it to the next hop. This totally shields the core network routers from the messy complexities inside the applications, allowing them to just route around physical failures super efficiently.
And modern provider networks, they've taken this routing efficiency to an almost unbelievable level. By using advanced traffic systems like segment routing, networks can bypass those heavy, complex routing lookups at every single stop. Instead, the network inserts segment identifiers, which are basically hyperspecific routing instructions directly into the packet header. Think of this like slapping bright, color-coded sticky notes on the outside of the envelope. The mail sorter doesn't even have to read the address anymore. They just follow the bright colors. The routers perform these lightning-fast label operations. They push to add a label, swap to change a label as it moves across segments, and pop to peel the label off when it reaches the destination. This highly tactical traffic engineering simplifies the protocols so much that the network can literally reroute traffic in a fraction of a second if a physical link suddenly snaps.
Which brings us to Section 6, the invisible framework. Tying it all together.
Let's bring this journey home. Here is the final piece of the puzzle, how the two systems actually talk to each other. When our packet from Toronto finally reaches the computer in India, the whole encapsulation process we talked about operates in reverse. As the data travels back up from the lower layer to the upper layer, each of those specific headers is carefully peeled off and processed. An entity from a given layer on System 1 is communicating directly with its exact peer entity on System 2. The Layer 4 transport protocol on the sending computer speaks exclusively to the Layer 4 transport protocol on the receiving computer. It's this beautiful, highly structured, collaborative interaction where adjacent layers within a system work together for one shared goal, the successful exchange of network traffic.
This layered, peer-to-peer interaction, it is the invisible machinery operating flawlessly every single time we click send, stream a 4K video, or load a web page. We are still heavily relying on this brilliant framework architected way back in the 1970s. But as we expand into this crazy new era of autonomous vehicles, sprawling artificial intelligence, and the Internet of Things, it leaves us with a really fascinating question. With billions of modern devices pushing the absolute limits of this invisible 1970s framework, what new layers will the Internet of tomorrow require to keep us all connected? Something to think about. Thank you so much for exploring the Protocol Layer Cake with me today. Keep asking questions, keep learning, and I'll catch you on the next explainer.